The variance of a random variable is a measure of how spread out or uncertain or random it is. A random variable with a high variance is very unpredictable, whereas a random variable with a lower variance is much easier to predict. So formally, definition, the variance of a random variable x is defined by this funny expression here. What I do is I take the random variable x and then I subtract from it its mean or expectation. I square the whole thing and then I take the expectation of that. Okay, so this is a little bit complicated here, but what I'm looking for is the idea that, hey, what's inside here is going to be big when x is far away from its expectation. So if I consider how far away x is from its expectation, I square it so that the negatives don't cancel out. The idea of the variance is that it's large if x is often far away from its expectation. So here's a quick example, just off to the side here. Let's say that x is a random variable with the property that it has value equal to -2 50% of the time, so I'm just using this PMF formula here. So the probability that x is equal to -2 is 1/2, and the probability that x is equal to 2 is also equal to 1/2. So we can check here that the expectation of x is equal to 0, and then the variance of x is equal to, okay, so half the time I'm going to have x equal to 2, and so I'm going to have 2 minus 0 squared. And then on the other side, half the time I'm going to have -2 minus 0 squared. So if I cash this out, I'm going to get 1/2 of 4 plus 1/2 of 4 again. And so each of those will become a 2, and then I'll add them together, so my result is 4. So this random variable has a variance that describes how far away it is from its mean. And in this one, we kind of did a really simple example to make sure it was easy to calculate. As you can kind of check on your own if you want, if instead of 2 and -2, I used 10 and -10, the variance would have been larger, reflecting the idea that even though in that example I'd have the same mean, my typical values of my random variable would be much farther away from that mean. Okay, so let's do a slightly more theoretical example. Let x be a Bernoulli random variable with probability p. What's its variance? Okay, so in order to calculate the variance of x, we first need to calculate the expectation. We actually know the expectation already. It's equal to p. And so this means that when we calculate the variance of x, we're going to take this expectation. We're going to use this formula here. And so what we need to do is consider the expected value of x minus p squared. We have two scenarios here, so x can have one of two values, either 0 or 1. So in the case that x has value 0, we need to consider the probability that x is equal to 0 times 0 minus p squared, and then the probability that x has value 1 times 1 minus p squared. This is our expectation formula. So here, the probability that x has value equal to 0 is 1 minus p times p squared. And then the probability that x is equal to 1 is p, 1 minus p squared. Okay, so are we done? We are not quite done. There's a little bit more simplification to do here. So if we look at what's going on, 1 minus p times p squared plus p times 1 minus p squared. So let's expand that out. So I'm going to have p squared minus p cubed plus p, and then I'm going to FOIL out the 1 minus p squared. So I'm going to get 1 minus 2p plus p squared, which is equal to p squared minus p cubed plus p minus 2p squared plus p cubed. Okay, so now a lot of things are going to cancel. So my p cubes are going to cancel, and one of my sets of p squareds is going to cancel. So I'm going to be left with p minus p squared, which is the same as p times 1 minus p. And that's my final answer there. That's my formula for the variance of a Bernoulli random variable with probability p. Its variance is p times 1 minus p. There's lots of other useful things to know about variances, and you'll work a few examples on your own. One thing we'll just note is that there's a useful theorem here about independent random variables. If x and y are independent, then it's the case that the variance of x plus y is equal to the variance of x plus the variance of y. So this is another case where this doesn't necessarily work if these random variables are not independent. I do need to check that before I'm ready to use a formula like this. Another thing that's also important to keep in mind is that this only works for addition. It's not the case almost ever that variances multiply even when the random variables are independent. So please keep that in mind as well. This theorem applies to addition, but not multiplication. So variances give us a way to quantify how random or spread out a random variable is. And we can use this in a variety of settings to measure topics like uncertainty. We use them in statistical hypothesis testing and many other settings as well.